Imagine a world hurtling through the infinite blackness of interstellar space, completely untethered from any star, its surface locked in eternal twilight or perhaps bathed in the faint glow of its own internal heat. No sunrise, no sunset, no familiar rhythm of day and night, just a solitary rogue planet drifting alone through the cosmos, carrying with it the faint possibility that life, against all odds, might still find a way to cling to existence. What if our own Earth one day became such a wanderer? Could anything survive the ultimate cosmic orphanhood? The very thought sends a shiver through the imagination, because it forces us to confront the fragility of life as we know it, while simultaneously opening the door to a universe far stranger and more resilient than our sunlit experience suggests. For centuries, humanity has gazed up at the stars, assuming that every living world must orbit a parent sun, basking in its life-giving warmth. But what if that assumption is wrong? What if the galaxy is teeming with rogue planets, silent travelers born from chaos? And what if some of them harbor the spark of life deep beneath their frozen crusts? Today, we embark on a journey into this shadowy realm of cosmic outcasts, exploring the science, the mysteries, and the breathtaking possibilities of life on a planet without a star. To understand the extraordinary idea of life thriving on a rogue planet, we must first step back and grasp what a rogue planet truly is. In the simplest terms, a rogue planet is a planetary mass object that does not orbit any star. It drifts freely through the Milky Way, unbound by gravitational loyalty to any solar system. These worlds are not rare anomalies. Astronomers now believe there could be billions of them in our galaxy alone, perhaps even outnumbering the stars themselves. Some are ejected during the violent early days of planetary formation, when gravitational tug-of-war between forming worlds flings the losers into interstellar exile. Others might be ripped away from their parent stars during close encounters in crowded star clusters or through the subtle gravitational nudges of passing stars over billions of years. Once cast out, a rogue planet becomes a ghost ship of the cosmos, sailing silently through the void at speeds of hundreds of kilometers per second. Its only company, the faint light of distant galaxies and the occasional glimmer of background stars. But without a sun to provide steady energy, how could such a world possibly support life? On Earth, virtually all ecosystems trace their energy back to sunlight. Plants capture photons through photosynthesis, fueling the entire food web from tiny microbes to massive blue whales. Remove the sun, and that cascade collapses almost instantly. Temperatures would plummet. Within weeks, surface oceans would begin to freeze. Within months, the atmosphere itself might start to liquefy or snow out onto the ground. Photosynthesis would cease. Most surface life would perish in a matter of days or years. Yet this is only the beginning of the story, because Earth and potentially other planets possess hidden reservoirs of energy that do not depend on starlight at all. Deep beneath our feet, in the crushing darkness of the ocean floors and the molten heart of the planet, entire ecosystems already thrive without ever seeing the sun. These are the realms of chemosynthesis, where microbes harvest energy from chemical reactions involving minerals, hydrogen, and sulfur compounds seeping from hydrothermal vents. On Earth's mid-ocean ridges, towering black smokers spew superheated water rich in dissolved metals, creating oases of life that support tube worms, clams, and bacteria in total darkness. These communities demonstrate that life can sustain itself on planetary internal heat alone, a crucial clue for rogue worlds. Now imagine a rogue planet roughly the size of Earth or slightly larger, perhaps one that formed with a substantial amount of radioactive elements in its core and mantle. As these elements decay over time, uranium, thorium and potassium release heat just as they do inside our own planet. This radiogenic heating, combined with residual heat from the planet's formation and any tidal flexing if the world has moons, could keep the interior warm for billions of years. A thick icy crust might form on the surface, insulating the ocean beneath like a planetary freezer lid. Beneath that ice, liquid water could persist, warmed from below by geothermal activity. Hydrothermal vents would continue to pump chemicals into the subsurface ocean, providing both energy and the raw materials for complex chemistry. In this scenario, life would not need sunlight. It could evolve in a dark, stable, chemically rich environment, much like the subsurface oceans suspected beneath the icy surfaces of Jupiter's moon Europa or Saturn's Enceladus in our own solar system. The rogue planet's surface might be a barren frozen wasteland averaging temperatures of -200 degrees Celsius or colder, but a few kilometers down in the hidden seas, temperatures could hover around 0 to 20 degrees Celsius, comfortable enough for liquid water and the slow dance of biochemistry. The thickness of that ice shell would be critical. Too thin, and the ocean might freeze solid as heat radiates away into space. Too thick, and it might trap heat so effectively that the interior becomes a pressure cooker, potentially sterilizing any nascent life. Yet computer models suggest a Goldilocks zone exists for worlds between about 0.5 and 10 Earth masses. A planet with a modest hydrogen-helium atmosphere, even just a few percent of Earth's atmospheric pressure, could provide additional greenhouse warming from below the ice or trap enough geothermal heat to maintain a liquid layer. Some rogue planets might even retain thick atmospheres of molecular hydrogen, creating a natural blanket that keeps surface temperatures surprisingly temperate despite the absence of starlight. In such cases, the entire surface could remain unfrozen, with oceans, rivers, and perhaps even weather systems driven by internal heat sources rather than solar evaporation. Imagine rain falling from clouds formed by geothermal steam, or lightning crackling in an atmosphere lit only by volcanic glow and faint auroras caused by the planet's magnetic field interacting with the interstellar medium. As we delve deeper into the possibilities, fascinating questions emerge about how life might actually begin on such an isolated world. On Earth, the leading theories for the origin of life involve either warm ponds on the surface energized by lightning and ultraviolet light from the young sun, or the mineral-rich environments of deep-sea vents where chemical gradients could drive the formation of the first self-replicating molecules. On a rogue planet, the surface origin pathway would be unavailable, but the vent scenario becomes even more promising. Hydrothermal systems provide not only heat and chemicals, but also natural proton gradients across mineral membranes, mimicking the energy harvesting mechanisms inside modern cells. Laboratory experiments have shown that simple organic molecules like amino acids and nucleotides can form under vent-like conditions, and mineral surfaces can catalyze the assembly of more complex structures. Over hundreds of millions of years in the steady, protected environment of a subsurface ocean, these building blocks could gradually organize into protocells, then simple microbes, and eventually more complex organisms. Without the disruptive cycles of day and night or seasonal changes, evolution might proceed at a slower but steadier pace, favoring organisms exquisitely adapted to chemical energy sources rather than light. What might such life look like? On Earth, creatures around hydrothermal vents have evolved bizarre adaptations. Tube worms with no digestive systems that host symbiotic bacteria converting hydrogen sulfide into energy, or shrimp with infrared sensing organs to detect the faint heat of vents in total darkness. On a rogue planet, life might take this further. Microbes could develop sophisticated chemosensory systems to track chemical plumes across vast subsurface oceans. Multicellular organisms might grow extremely slowly, conserving energy in an environment where food is sparse but stable. Some might bioluminesce, creating their own faint light shows to attract mates or prey, turning the dark waters into living constellations. Others could harness the planet's magnetic field for navigation or develop pressure-resistant bodies to thrive near the crushing depths above the core mantle boundary. If the rogue planet possesses a strong magnetic field generated by a molten iron core kept liquid by internal heat, it could shield any potential atmosphere or subsurface ocean from the harsh cosmic rays and stellar winds of interstellar space, providing another layer of protection for fragile biochemistry. Yet the challenges are immense, and we must not romanticize the scenario. Cosmic radiation would bombard the surface relentlessly without the protection of a stellar heliosphere. Micrometeorites and interstellar dust could pepper the icy crust over eons. The planet's isolation means no delivery of fresh cometary material or meteoritic organics after its ejection, so all the necessary elements for life, carbon, nitrogen, phosphorus, must have been present from the beginning. Temperature fluctuations driven by varying geothermal output or occasional close passages near other stars could destabilize the delicate balance keeping the ocean liquid. And if the rogue planet is too small, its internal heat would fade too quickly, freezing the world solid within a few billion years. Larger worlds, perhaps super-Earths with more massive cores, might fare better, retaining heat longer and supporting thicker, more stable ice shells. Recent discoveries of free-floating planetary mass objects in star-forming regions like Orion and Rho Ophiuchi suggest many rogues are indeed massive enough, with some estimates placing their numbers at trillions across the galaxy. Microlensing surveys by telescopes like Hubble and the upcoming Roman Space Telescope are beginning to detect these ghostly worlds by the way their gravity briefly bends the light of background stars, revealing a hidden population far larger than previously imagined. Pushing the boundaries of speculation, some scientists have proposed even more exotic possibilities for rogue planet habitability. What if a rogue planet captures a small moon or asteroid belt during its wanderings? The resulting tidal interactions could generate additional internal heat, much like the tidal heating that keeps Io volcanically active in our solar system. Or perhaps a rogue world passes through a dense molecular cloud, accreting a fresh layer of organic-rich ices that could later melt and deliver nutrients to the subsurface. In the far future, as the universe ages and stars grow scarce, rogue planets might become the last refugees for life, their internal warmth outlasting the final red dwarfs. Advanced civilizations, if they exist, might even engineer their own rogue habitats, deliberately ejecting planets or building artificial ones powered by geothermal or fusion energy to survive the death of their parent stars. The concept blurs the line between natural and artificial, raising profound questions about what we mean by a living world. As our journey through this cosmic wilderness continues, we encounter ideas that challenge our very definition of habitability. The traditional habitable zone around a star, that narrow band where liquid water can exist on the surface, becomes irrelevant for rogues. Instead, the habitable zone shifts inward into the planet itself, defined by the depth at which geothermal heat balances radiative cooling through the ice. Life here would be decoupled from the galaxy's stellar cycles, immune to supernovae, gamma-ray bursts, or the gradual brightening of stars that will eventually boil Earth's oceans in a few billion years. A rogue planet could theoretically remain habitable for trillions of years, long after the Milky Way has merged with Andromeda and most stars have burned out. This longevity makes rogue worlds potential arks for life, carrying biological information across the vast emptiness between galaxies over cosmic timescales. Perhaps panspermia, the transfer of life between worlds, occurs not only via meteorites within solar systems but also through the rare collisions or close encounters of rogue planets themselves, though such events would be exceedingly uncommon. Yet even in this optimistic picture, the silence of the void raises haunting questions. If life can arise and thrive in darkness, why have we not detected biosignatures from rogue planets? The answer lies in the immense difficulty of observing them. These worlds emit almost no light of their own, appearing only as faint infrared sources if their surfaces or atmospheres retain any warmth. Detecting subsurface oceans or atmospheric biomarkers would require telescopes of unprecedented sensitivity, perhaps future generations of space-based interferometers capable of resolving objects light years away. Current missions like JWST have begun probing the atmospheres of distant exoplanets, but rogue worlds remain elusive phantoms. Their very isolation makes them hard to find, yet that same isolation might protect them from the catastrophes that periodically sterilize star-bound planets. A rogue planet's life, if it exists, could evolve in peaceful obscurity, developing intelligence without the pressure of stellar variability or asteroid impacts from a crowded system. What kind of minds would emerge in such eternal night? Would they dream of light they have never seen, or would their philosophy center on the steady pulse of geothermal rhythms and the chemical whispers of their hidden seas? The implications ripple outward into astrobiology, philosophy, and even our search for extraterrestrial intelligence. If life is common on rogue planets, then the total number of habitable environments in the galaxy skyrockets. The Drake equation, which estimates the number of communicative civilizations, might need a new term accounting for starless worlds. Contact between such civilizations would be extraordinarily difficult, separated not only by distance but by the relativistic speeds at which rogues travel. Messages or probes would need to anticipate a planet's trajectory centuries in advance. Perhaps the first evidence of alien life we ever detect will not be a radio signal from a star system, but a faint chemical anomaly in the spectrum of a passing rogue, or a strange object entering our own solar system from interstellar space. The recent interstellar visitors Oumuamua and Borisov have already hinted at the traffic moving through our cosmic neighborhood. What if one of those objects carried frozen microbes from a long-lost rogue ocean? As we approach the end of this exploration, it becomes clear that rogue planets are not mere cosmic castaways but potential crucibles for a different kind of life, one forged in darkness and sustained by the planet's own beating heart. They remind us that the conditions for biology may be far more diverse than our sun-centric biases allow. Life, it seems, is opportunistic, stubborn, and capable of exploiting energy gradients wherever they persist, whether from a blazing star or the slow decay of radioactive atoms deep underground. The universe may be filled with silent, ice-shrouded worlds where strange ecosystems pulse in eternal night, evolving stories we may never fully read. Our own Earth, so dependent on its parent sun, might one day face ejection if a passing star disturbs the outer solar system. In that distant scenario, humanity's descendants would need to retreat beneath the ice, harnessing geothermal power and artificial light to survive, becoming stewards of a rogue world themselves. And so we are left with a profound and slightly unsettling reflection. What if the majority of living planets in the universe are not the luminous blue-green worlds orbiting gentle stars, but these dark wanderers carrying their fragile cargo of life through the abyss? If that is true, then the cosmos is far lonelier and more mysterious than we ever imagined, yet also more alive in its hidden depths. The next time you gaze up at the night sky, remember that among the countless points of light, there drift unseen worlds, silent and self-contained, where life may be quietly thriving without ever knowing the warmth of a sun. Could such a planet be out there right now, its subsurface oceans teeming with beings that have never seen a star and never will? And if we one day encounter evidence of them, or if our own world becomes one, what would that reveal about the true nature of life and our place in this vast, indifferent, yet strangely hospitable universe? The rogue planets wait in the dark, holding their secrets, challenging us to expand our vision beyond the light and into the shadows where life might burn brightest of all.